Okay, hey everyone, and welcome to yet another RO Theory seminar. We've got Tengyang with us this week to speak about the role of coverage in online reinforcement learning. Tengyang is currently a postdoc or postdoctoral researcher at Microsoft Research and will be joining UW-Madison as an assistant professor of computer science soon. And together with Tengyang, we've got Andrea to host this week. Andrea, do you want to say hi to everyone?
Hello, everyone.
So you'll be hearing a lot from Andrea, and yeah, Tengyang, please do get started.
Yeah, so thank you so much for the kind introduction. Yeah, I'm very happy to be here. And my name is Tengyang Xie. So today I'm gonna introduce our work in ICLR 23, the role of coverage in online reinforcement learning. So this is a joint work with Dean Foster, Nanjiang, Yubai, and Shanghai. So let's get started. In this talk, I will mainly cover three results and starting with the problem setup. So the three results is, the results are listed here, and you will hear them all soon. And let me set up the problem first. So we are still studying the problem of reinforcement learning. I guess everyone should know well on that. We have a environment and a learning agent. So at each at each state X, our learning agent run some action A by using a policy pi, and then it receives some reward R, and the environment translates to the next state. And the learning goal of reinforcement learning is to find a best policy to maximize the cumulative reward. So here are some detailed notation I will use over this talk. So we study the episodic MDP, where we use the capital X to be the state space, and the lowercase x to be the state. And also A is the action, H is the length of horizon, P is the transition function, and R is the reward. And also we use S1 to denote the initial state. And also, I will use this term of value function in this talk, where J of pi is the cumulative return of running policy pi, so that the pi star is the max optimal policies that have the max J of pi. And also the QH pi here is the Q function at time step H, which means at time step H, starting from state X and action A, we run policy pi. What is the expected return of that? And also another important notation I will use is the Bellman operator, where I use the TH to be the THF to be the Bellman backup of some value f, which is computed in this way, reward plus the expected value at next time step. And also over this talk, I assume reward is normalized, but it should be easy to generalize that, yes. And also in this talk, we are motivated by how can we build some connection in between online and offline reinforcement learning. So therefore, let me quickly refresh. So what is the basic of online and offline reinforcement learning? So over the past years, there are actually these two lines are very popular, but most of the work are studying them separately in parallel. So in online reinforcement learning, the typical learning protocol is here. At each episode, from 1 to the capital T, what learner do is the learner first pick a policy pi t, and then execute it. And therefore, the learner also receives some new data, which is a resulting trajectory. So the learner can using the new data or the all existing data to pick another policy and repeat that, so on and so forth. And the learning goal of online reinforcement learning is we want to minimize the regret, which is we want the sum from 1 to the t, the gap in between the pi star and pi t to be as small as possible. So on the other hand, offline reinforcement learning is different. So in offline reinforcement learning, there is no interaction access here, but we provide the learner a offline data. So also in this talk, I will use DH to be the offline data at layer H, which is actually NID tuples from some data distribution mu. So actually mu is a distribution of X and A, and R and max state are from the reward and transition function. And the learning goal of offline reinforcement learning is basically like we want to output a policy that as close to our pi star as possible given the offline data. And also in this talk, I will mainly focus on the model-free reinforcement learning with general function approximation. That is, like, we don't want to estimate the transition, and we will provide a learner a value function class, which is defined here. And for each layer, we also assume that is like bounded, but also easy to like generalize. And also, what we do is mainly the value base, like we don't have a separate policy class. So the policy I use in this talk is the greedy policy induced by our value function. And I use this capital pi f to be the all possible greedy policy based on our value function class f. And we also rely on this like standard assumption, completeness assumption, basically saying that one step bounded backup of fh plus 1 for any h plus 1 in its like level is also in the like fh, the function class in the last level. And this one can also imply the standard realizability assumption. So that's all the problem set up. Questions? Okay, great. So yeah, so now let me go to the first result, which is also the main result of this talk. That is like we will introduce coverability. I would say is a coverage condition of online reinforcement learning. So before introducing the details, maybe let's quickly refresh what is the like usual learnability conditions in reinforcement learning, particularly in online and offline reinforcement learning. So in online reinforcement learning, people usually introduce something called the structural assumption. For example, the like low rank transition, low Bellman rank, low Bellman eluder dimension, or something like bilinear rank, or there is a long line of that. And I would argue most of them rely on the use of elliptical potential lemma, which indicates that most of them are like linear in some way. On the other hand, offline reinforcement learning do such thing very differently. People usually use something called coverage condition, or technically concentrability condition. I will tell you later. The idea behind of that is, say that if we say we require a uniform coverage, that is saying our offline data covers roughly all reachable regions. And also in recent years, there is also some more advanced one called single policy coverage. That is, we only assume our offline data covers some good policy, for example, pi star. And one of the main questions in this paper or in this talk is, can we use the coverage condition to bring some new understanding to the online reinforcement? Okay. So before talking about the coverage condition in online reinforcement learning, maybe we need to define what's that in offline reinforcement learning. That is the so-called concentrability condition. So this one is one of the most standard way to define that. That is like, what is the worst case density ratio between d pi over mu among all pi in our policy set, capital pi. So for example, like, where mu is our offline data distribution. So for example, if in this example, like if our policy class have 4 different candidates, where the x-axis denotes like different choices of state and action, y-axis to denote the density, then let this like blue shadow to be some offline distribution mu. And therefore, the offline concentrability is roughly the ratio in between this like max density over the density of mu. Okay? And motivated by that, we can define the coverage condition in online RL. That is, if we have full flexibility of choosing the data, if we have full flexibility to choosing the data distribution, what is the best possible concentrability or density ratio we define in this way is we call it online coverability. So if we are still using this example, what we do is like we first find some best possible data distribution, and then the like ratio in between of these two is defined by is the definition of the coverability. So questions? So the idea behind this coverability is to measure like how difficult our MDP is being covered. And we would argue that should play as a like complexity measure of our MDP. For example, just in this case, imagine if our four policy have a large overlap, then it should be easy to find a distribution that have small ratio, which means the problem is easier. On the other hand, if all policies are far away from each other, therefore that ratio cannot be small. So that's the intuition behind of that. So after defining coverability, one natural question is that sufficient for sample efficient online reinforcement learning? And the answer is yes, by using a classical algorithm GOF introduced by Jin et al. 2 years ago. So the algorithm GOF have a pretty clear idea in it. That is, for every time step H, our learning agent mainly do two things. It first compute a optimistic policy pi t. And in GOF, the way is called initial state optimism. That is, it built a virtual space and then find the most optimistic one based on its like initial state. And therefore, GOF runs such pi t, get some new data, and return to the like compute optimistic policy part, and so on and so forth. And also note that in GOF, they use the empirical Bellman error to construct this virtual space or confidence set. So the main result in our work is like we have showed under completeness assumption, the algorithm GOF has this nice regret, which is root T times root C cover, where cover is the coverability we just defined before. Questions? Okay. So after we have this low regret result,
let me ask you,
sure.
Can you remind us the definition of coverability?
Oh, sorry, yes, it is here.
Maybe a couple slides back, yes.
It's just here. Something like if you have freedom to pick any data distribution, what is the smallest possible concentrability?
Any mu distribution, yes. Okay, so there exists a distribution mu.
Yes, yeah, it exists, but you don't need to know that.
You don't need to know that. Yeah, GOF doesn't have that as input,
yes.
So it's. I see. Okay, thank you.
Sounds good. Yeah, so maybe after that you may want to ask, what does that mean? Like, what can that implies? So let's try to understand coverability. And I would say one of the most important property of coverability is like it has a equivalent definition, and I would call it cumulative reachability. So recall the definition of coverability is this. We now define another thing, cumulative reachability, That is, we do integral over state X and action A by using the largest possible density over our policy class. So if we come back to our previous example, the cumulative reachability is roughly the mass of all these blue region, where we only count every place once, even for this overlap region. So why it is like equivalent to the coverability? That is because if we want to find the best possible data distribution, we have shown that the distribution is just we normalize this blue region using their total mass. That is here. We just press that blue region to ensure that it's normalized. Therefore, it is easy to show that the value of the cover is actually same as the total mass of this blue region.
So Tengyang, I have one question. So I have one question, if you don't mind.
Sure.
If you go back to the main result, so you say in the regret, you prove a regret bound for golf, which is a function of this coverability parameter. But I think the basic question that they have is this. The authors on golf, they have a result as a function of the eluder dimension, right? When that quantity is small, is your quantity here also small?
Oh, I think that's a great question. I'm not sure, but I think like in general, coverability and Bellman eluder dimension are two like orthogonal stuff.
I agree, because basically the way these temporal difference based methods proceed the analysis is they really look at the Bellman error. But the distribution, like it could be, it could be very, very big, right? You could visit the dynamics could be very complex. So your result is kind of, a new result in a certain, right?
Yeah, I would say they are mostly like orthogonal, and I will also show you some example that when Bellman eluder is large, but this one is more.
I see. Okay, thank you so much.
Yeah. So this is the first important property, is that coverability is essentially the same as cumulative reachability, and actually that play an important role in our proof. I will show you later. And another question is, when is coverability small? So I would argue that coverability is a natural generalization of the latent state space. For example, like in contextual bandit, the latent state space is 1, so that the cover can be bounded by the number of actions. And also in the example of exogenous block MDP, where which is roughly like block MDP with some very hard to control exogenous noise. And in this case, actually neither of the Bellman eluder dimension or the bilinear rank can capture this instant, but the C cover is also bounded by the number of latent states times action. And the idea behind of that is, if we have a bounded latent space, then the density of every state and action cannot be too large. Therefore, we can bound C cover of that. On the other hand, although C cover looks orthogonal to the low rank style assumption, actually by Aldridge, Lin, and Nan, I think that work has presented in the same seminar last month, have shown that C cover can be bounded by the dimension of low rank MDP times A. And actually, this result implies some interesting things, that the Q-type golf actually is efficient for low rank MDP with a root T regret bound. And for the Q-type and V-type stuff, that is a little tricky. That is for the Q-type algorithm, I think that is firstly introduced by Jin et al., the golf paper. Here, the Q-type means once we have a optimistic pi t, what we execute is pi t itself. On the other hand, for the V-type, what we execute is for first 1 to h-1 step, we execute pi t, but for the last step, we execute the uniform action, uniform over the actions. And in original golf paper, they only showed people only know that usually they want to cover the low rank style assumption, we need to use the V-type algorithm, and therefore we cannot get the regret bound of that. And by using the definition of coverability, we first know that even for the Q-type golf, can also do low rank MDP and have T regret. Questions?
So by low rank MDP, I guess you mean the representation learning setting.
Yes. We don't know the representation.
You don't know the fee, but it is contained. I see, right. So previously, I think that setting, we only know that the V-type would work, but the coverability result shows that Q-type also works in that setting.
Yes. Okay. So now I will play with some math and show the proof idea. Why is coverability sufficient? Okay. So we will first start from the standard regret decomposition, which can be easily got from the optimism argument. And where over this talk, I will use delta to be the Bellman error, so that we can decompose the regret to be the on policy Bellman error over our episode. And after that, we do a Boolean and stable decomposition. That is, we define this tau xa, which means at which time step in expectation we will get enough samples for some state x and action a. And in terms of the enough samples, we determine this mu h star to be the best data distribution. Therefore, by definition, all density, all d pi cannot be larger than the C cover times mu star. And also the dt tilde here is roughly the cumulative data distribution at time step t. Okay.
So Tengyang, mu star is the one that minimizes concentrability, right?
Yes.
The worst case concentrability. Yeah.
Best case.
Yeah, the best distribution. Yes.
Yes. Okay. Yes. So that we now use a indicator in terms of this tau h to determine our regret, where the left part is the Boolean phase. It only counts how much regret we pay to get the Boolean samples, which can be bound using the definition of tau by Q times C cover. And the right part is, I would call it stable phase, and that is the next goal, how to bound that. Okay. So now let's bound the stable phase, which is which is here. So we first use some the Cauchy-Schwarz style argument to change the measure by adding this term of cumulative d tilde. And therefore, we run Cauchy-Schwarz to change the measure, where the last term is essentially our definition of the radius of confidence set or version space, which is bounded by some constant as we use in the golf algorithm. So our next goal is to bound this extrapolation error. Okay.
Tengyang, one sec. So why is the second term bounded?
Oh, because that is the expected Bellman error over your historical data. The definition of the version space in golf.
But so that quantity will be bounded by the eluder dimension?
No. If you only count, maybe shall I come back to the golf algorithm?
Up to you.
Yeah. So So you can see in golf algorithm, this term is basically this one.
Which one?
This epsilon h is the empirical version of that term. Your empirical Bellman error over your historical data.
Yes.
Yes, and the reason you need to use eluder dimension is to control the on-policy Bellman error which cannot be captured using your data, right?
So how are you bounding that term? Like, by what is it bounded?
I mean, these two terms. I mean, like that. I mean, this term is just the expectation of the definition of the I mean, the radius of virtual space in Gauss algorithm. You just need to use the concentration inequality to bound that.
Yes, so this term only has an on data estimation error, right? It has nothing to do with change of measure going out of your distribution and so on. This is literally like the error you've seen on the data distribution you have trained.
I see.
Yeah, because the first term is roughly you change your measure from the on policy one to your data distribution.
Yes, if you talk about eluder and these how well do you do out of the distribution, it's more like the first term instead of the second.
Right. I see. Okay. Thank you.
Okay. So let's now talk about the first term. So the first term is roughly the density square of your on policy density over your cumulative data distribution from your data. So at first step, we leverage the definition of tau h, which says that our d tilde h here will be at least this large. So we have something like so we have this one, and the reason we do so is we want to ensure the denominator is always larger than the d pi h for any pi. And after that, we relax the one dth using their maximum. And if you remember our cumulative reachability definition, this term is actually can be bounded by the cumulative reachability. That is exactly the definition of that. We pick the largest possible density for each x and a and do the integral over them. So we are good for this term, can be bounded by C cover. And for the first term, that is actually the per state action elliptical potential, can be bounded by log t. Note that we don't have sum over x and a here, we take the max over them. So we just take the elliptical potential argument and that's bounded by log t, and so we are done. And maybe one thing I should emphasize is the key novelty of here is we explicitly leverage the density square, whereas in most of the prior work, they usually either use the average Bellman error or relax the squared Bellman error to the average Bellman error. Then they don't have this density square over density term. And that is the key difference. And the new information we get from it is we may want to use the squared Bellman error explicitly in both algorithm and analysis to get tight bound. Okay? Questions? Okay, so that's pretty much for our first result, also the main result. And let me summarize it. So the first takeaway of that is coverability is sufficient for low rank online reinforcement learning via the algorithm GOF. And also there are many cases can induce low coverability. For example, exogenous block MDP, low rank MDP. And also this give us some new interesting implication. For example, the Q-type GOF can achieve root regret for low rank MDPs. And also we know that we may want to leverage the squared Bellman error explicitly in the algorithm and analysis. The reason is we want to use this density square over density in our analysis. Okay? So questions? That's all for the first part. Okay, so let me turn to the second part. So the second part, we mainly ask the question, can we use some weaker notion of coverability in online reinforcement learning? And we will mainly study the idea of using the so-called test function, and that is close to the idea that's like Andre just mentioned, like can we control the Bellman area rather than density? And partially the answer is no, and I will show you here. So let's start with some easy case, single policy coverage in offline reinforcement learning. So that is a much weaker assumption than the uniform coverage, where we only want to cover the density of high star rather than all policy. However, its online version is actually trivially impossible. The reason is here. If we have full flexibility to picking our mu, we can actually picking the mu is equal to, sorry, that should be d pi star, and which implies the online version of this case will be always 1 for any MDPs. So that is impossible. So we come back to this uniform coverage style. And we just added this per state action case. And now how can we use the test? How can we use the function class as the test function? By Wang et al. And Benet et al., they have tried to see like in offline reinforcement learning, they can use the something called feature coverage, which essentially saying that the covariance matrix of all the pi can be covered by the covariance matrix of mu and times some constant. And also in offline reinforcement learning, there is even a more flexible case by Chen and Jiang and also myself that is using the general function class as the test function, which is saying that the Bellman error, the squared Bellman error over d pi cannot be can be actually bounded by the squared Bellman error over data distribution mu for all f and for all pi. And in the next part, I will tell you the online version of this general function class case is actually impossible. Okay, questions? So the informal statement is like this. The following condition, also with completeness, is insufficient for online reinforcement learning. Where the condition is here, there exists some mu star such that for all pi and for all f, the squared Bellman error over d pi can be bounded by some constant Cgn times the squared Bellman error over mu star. Oh, okay. So now let me tell you the.
Tengyang, can you go back one second? So why is this theorem showing this thing is insufficient? Like
Yeah, I will show you later.
But no, why is the statement?
No, it's not. It's saying that the following is insufficient. Like, what does insufficient means is not.
Okay.
Insufficient just I think basically it says that if you only assume this, you cannot have a online polynomial results that scale with this version of CJ.
Yeah. Thank you.
Yeah. Thank you. Yeah. So the lower bound is, construct function is roughly here. So suppose we have a H-level binary tree as our MDP. So I will only use 3 level here, but we will have H-level in our construction. And also consider the following function class. Formally is defined here. So what does that mean? It means for each level H, for every function, it will only have value 1 for one pass, and the others will be value 0. For example, like in this level, there will be a function for F3, where each one only have one of these paths is value 0 and all value 1, and all the others is value 0. And Q star is this one is 1, all the others are 0. Oh, and also by the way, I forgot. So in this tree, only one path have reward 1, and all the other paths have reward 0. Okay. And it's easy to show that in this case, for any online RL algorithm, complexity will be exponential over h. That is because we don't have any info of which path is good and which is bad. So we essentially need to try all of them, okay? However, if you consider this pi star as the best data distribution in terms of bounding this term, we can show that actually for any function that is not Q star, this squared Bellman error over mu star will be at least 1. The rough region is here. For any f that is not equal to Q star, there must be one path in this green path that have the value of 0. However, since it have reward 1 in the end, it will imply this error will be at least 1. On the other hand, since we only have h level in total, which means the max possible Bellman error is at most h, as that is at most 1 for each level. Therefore, we can show the Cgen in this case is actually h, but it has exponential complexity for online reinforcement learning. Okay. Okay. So yeah, so that's maybe the most of we have for the second part. We also have 3 main messages. The first one is the single policy coverage is trivially insufficient for online reinforcement learning. And also we would argue that the interplay in between online and offline coverage with mainly general test function are is pretty nuanced. And also the understanding of how can we use test function to generalize coverability is still quite open. Okay. Okay. So now I will go to our last part. I will revisit the existing complexity measure in online reinforcement learning and mainly digest the difference, like what is the insufficiency in existing complexity measures. Okay. So I will mainly use the Bellman eluder dimension as an example, and that argument can be also generalized to the others. So informally, Bellman eluder dimension is defined by the longest length of this sequence. That is, we can pick delta to be the Bellman error of any function in our function class. And also the d here can be picked as d pi for any pi where in our pi class. And then the sequence is at each time step t, we have low Bellman error in sample, but larger Bellman error in the unpolicy case. And also one thing I would like to emphasize is in the definition of Bellman eluder dimension, the Bellman error here are all using the average Bellman error rather than the squared Bellman error. And actually, I would argue that is the first insufficiency of the Bellman eluder dimension. So we have a proposition like that. That is, there exists an MDP such that C cover is O1, but Bellman eluder dimension can be exponentially large. And also, we can argue the algorithm Olive, which is also an initial state optimism algorithm based on the average Bellman error, also suffers this exponential complexity. Okay. So the idea of the lower bound is. Oh, go ahead.
Well, not really. Like I was just trying to parse what's happening. So you have an MDP with small coverability, but very large Bellman error. What does this tell you?
Sorry, it's like
Bellman-Eluder dimension.
Yes.
What does this tell you?
I'll tell you that like basically like the coverability, like one thing is the line of coverability and Bellman-Eluder are two like orthogonal stuff. Another is like another thing is like the definition of Bellman-Eluder have some like, I mean there is some place can be improved, and I will tell you later.
So basically what you're saying here is that, for example, you take a problem which is a small coverability, but the Bellman-Eluder dimension is larger. And if you apply the old result for the golf algorithm, for example, they will predict that the algorithm will take forever to learn. But your result can say the algorithm can learn very quickly.
Yes, exactly.
Okay, so that's what insufficient means. Basically.
Yes.
Okay, thank you.
Thank you, yeah. So the intuition of this lower bound is roughly like the pointwise control, which is by the squared Bellman error, is much stronger than the average control. Think about if you want to control a sequence of xi, one is you use like their average, one is using their squared sum. Of course, the second one is much stronger. So that we can use the idea of exogenous block MDP to construct the lower bound. And I will not show you the construct function here since that's a little long, but it satisfies the following properties. The first one is the cover is actually 1, which means we only have one latent state here. However, in terms of the average Bellman error, it has this stuff. That is, as long as your f and g are different, and also neither of them is q star, then the Bellman error of g on the distribution of f will be 1/2. Okay? So that we can use this example to construct a sequence that can violate the Bellman-Eluder dimension. That is like we can just pick any order of the function class, like f1, any order of the function class minus q star to be our value function class, and also we use dt to be the on policy distribution, and then we can have like at each t the average Bellman error on policy is 1/2, but in data is all 0. Okay? And this means for epsilon equal to 1/2, Bellman-Eluder dimension can be exponentially large. Okay? So after the first one, we would also argue there is another insufficiency of existing definition. That is the incorrect dependence on skew. So for the first one, we have some, there is a natural question that is, can we use a squared version of Bellman-Eluder dimension to improve that? That is being said, if we change the in-sample error from the average Bellman error to the squared Bellman error in this part, is that good enough? So we would still argue the answer is no, that is not good enough. Although squared Bellman-Eluder dimension can break that lower bound before. The intuition here is maybe let me tell you the like average result first. So after introducing that, we can still find 2 MDP class such that for the MDP class 1, there is a lower bound for its regret that is can be at most t/2/3. And in this case, both C cover and squared Bellman-Eluder dimension can capture it correctly. However, for the class 1, it can have UT regret for golf, and C cover can capture the property of this MDP. but squared Bellman, but yes, the squared BE still cannot capture that. And the reason or intuition in behind of that is, for the definition of squared eluded dimension, no matter our violet is epsilon or 1, that will always count the same in it. And that's the reason why it costs insufficient. Okay? Okay. So after we talk about those like orthogonal and insufficient stuff, at last I will introduce another complexity measure called sequential extrapolation coefficient, or in short, SEC, which could subsume both coverability and also Bellman eluded dimension. The definition is here, which is a little complicated, but the main idea behind of that is we use the ratio between the on-policy error and in-sample error to be the surprise at time step t, and we assume the total surprise over t to the 1 to capital T cannot be very large. Okay, and we can show that golf is also small in terms of this SEC definition. And also for both coverability and Bellman eluded dimension, this SEC is more for both of cases. Okay. So yeah, so that's also all for our last part. And we have some takeaways. The first one is like the using of average Bellman error is one insufficiency of existing complexity measure. And the second one is like Bellman eluded dimension actually using an incorrect dependency on skew. And we can fix them by introducing our new measure SEC, which could also unify the both coverability and Bellman eluded. So that's it. Questions?
Thank you, Tengyang. So yeah, we'll have questions that are recorded at first, and then if we run out of questions, I'll stop recording and you can feel free to chat away.
So should I read the question or so?
Yes, I think someone had an answer, but I don't know where a question, but I don't know where they went.
Oh, I guess Audrey's question is like the in the upper bound result, we only use the equivalence of coverability is same as cumulative reachability. Is that the stuff?
Yeah, that's my question. Sorry, a lot of background noise right now. But yeah, it seems in the upper bound proof, you only use like one direction of this equivalence. And I was asking if you use the other direction.
I think like most of that is, but not really. Like in this per state action elliptical potential lemma, we need to use this part is larger than all the pi.
I see. Okay. Yeah, I
Yes.
got it. Thanks. Thank you.
Yeah, but maybe I think that is but I would still say that is an interesting observation because I think like essentially think about why coverability captures the difficulty of exploration. I feel like this definition is more intuitive. Like the more mass we have, the environment should be harder to explore, since we have more region to be reached.
Yeah.
Okay. Questions?
It's pretty impressive that golf can work better when like eluder dimension is high and comparability is low.
Yeah.
I find that a bit interesting because.
Well, I think a part of the problem is that these algorithms, either Golf or Olive, I mean, when they are first proposed, they come together with a complexity measure, but the algorithms themselves are extremely generic, right? They're not necessarily tied to that complexity measure proposed along with them.
But my confusion is that you do have exploration bonuses, right? And somehow what they have in mind is that those algorithms, they exhaust all the exploration bonus in the sense that they search in all directions in the function class, right? And that's.
I mean, Golf is just being optimistic at initial, right? Golf doesn't do bonuses.
No, I agree. It doesn't do bonuses, but shouldn't that be sort of similar?
Yeah, kind of.
Yeah, I mean that's interesting. It's non-obvious that. Yeah, it's kind of unexpected, I would say, that it would work much better than the result that is there. So, yeah, I'm glad you figured it out.
Questions?